Evening all, we're Group 5 and this is our L3 build presentation. So these are all the parts used in our robot. Now it looks like there's quite a few, there's actually only 8 different parts because triangles are very symmetric, so it makes our design simple. And I'll tell you how they all fit together and function. Simplicity was our aim, and there are many parts, there are very few. So let's look at what we envisaged and compare it to what we actually have now. Our initial design was 10 grams too heavy, so it's gone on a New Year's diet. The top platforms have been thinned, so that's the new one and that's the old one. And you can see the bottom has actually been removed with sections entirely, and that's saved 8 grams. The motor was too heavy, so that's been changed, as has the circuitry. More in a minute. So we looked at all we could do, and we chose 3D printing and laser cutting. 3D printing for the rubber, laser cutting for the non-rubber, because both are very accurate, very time-saving, and saves in tooling. And super glue was used because it's easy, readily available, and suitable for this scale model.
We chose acetal for the main platforms and rubber feet because they can be manufactured easily and are also lightweight. Carbon rods were used for the main structural supports due to high specific strength. Looking at the finite element analysis, we can see that all the materials work together at the designated dimensions and stresses. This animation shows us the final assembly of our robot. We have undergone 3 major changes when compared to the ideas presented in our design presentation, all of which makes use of circuitry from a toy helicopter for practical and time-saving reasons. Firstly, the engine has been swapped. The old one was too heavy and accounted for 40% of the weight limit, making the initial design unfeasible. It was then changed for a smaller, lighter one for the toy. This is a physical comparison of the old motor and the transistor pair with the new one. The light dependent resistor that we were using has also been changed. It worked brilliantly so long as you could hit the target area with an IR beam, which proved too difficult. This has been swapped for the remote controls for the toy. Finally, the electronics had to be changed so that the other components from the toy would work reliably. This also solved the difficulty of us building everything from scratch. Our design was predicted to jump a distance of 4.6 meters in 1 second, reaching a peak height of 1.15 meters. We conducted a vertical jump test and extrapolated the results at a 45-degree angle. We expect a jump of 1.05 meters long. Therefore, the actual jump performed by our robot was 78% shorter than it was originally designed for. This difference is partly due to modeling inaccuracies, with the biggest factor being weight. The second prototype was still too heavy. We will continue to optimize our work by the final jump test. And this is our robot in action. Thank you for your time.